rivers.
What is this technology?
Essentially, we're drawing oceanic rain systems that exist over the oceans into geographic targets, into our agricultural areas. The technology uses electromagnetics, so we're not interfering with the atmosphere or with the environment. We're not damaging it. We're not using chemicals fired through rockets like other technologies use. We use a very gentle but powerful technology, launching electromagnetics into the atmosphere to modify the flow of the weather system over the ocean and drawing it into a target. So to try and keep it simple, we establish some kind of link with a weather system, and once we've seen through satellite meteorology that we have that link, we're able to draw that system in incrementally towards the target, such as in this case the Horn of Africa.
Alright guys, we're going to learn about microwaves and its effect on water and the evaporation of water vapor. Alright, so difference between boiling and evaporation. Because you see, some people say, well, it's going to send up the clouds, it's going to, we'd have to boil them. No, you don't have to boil to have a loss of water vapor in the environment. So you have boiling, a process in which a substance changes its state from the liquid state to the gaseous state. It's fast, bubbles are formed, occurs throughout the liquid, occurs at a definite temperature, boiling point, source of energy needed. Evaporation. It's a process in which a substance changes its state from the liquid state to the gaseous state without boiling. Slow, no bubbles formed, takes place only from the exposed surface of the liquid, occurs at all temperature, energy supplied by surroundings. Okay, so there's that. Okay, microwave and infrared. How microwaves heat. Alternating electric field. Plus, minus. Plus, minus. Space charge polarization. Orientation polarization. Okay. Alright. When the material to be dried is conveyed through a microwave field, the water molecules in the material reorient constantly to align with the changing field. This movement generates heat inside water molecules and makes entire mass of water to evaporate it uniformly without heating the product externally. Most important, microwave frequencies to be used for heating. 915 plus or minus 13 megahertz. 2450 plus or minus 50 megahertz. So that's in the 2.45 and 0.45 and 0.9. Alright, it can be used for drying of different products like food, textile, chemical, pharma, foundry, core, etc., clouds. And they didn't say that, but hey, why not throw that in? That's just a little water vapor if it could do all the rest. Microwave is also used for heating and curing of different products as well as microwave-assisted reactions of chemicals. Alright, water and microwaves, dielectric constant and polarization, complex dielectric permittivity, Okay, we're not going to do all of that right now. Liquid water absorbs microwave radiation strongly enough to enable cooking. Right? The radiation left over from the Big Bang is the same as that in your microwave oven, but very much less powerful. Stephen Hawking. Okay. So he says, water and microwaves. The microwave oven is part of modern life, but how do the microwaves interact with water and food to efficiently heat the food? The water dipole. Dipole attempts to continuously reorient in electromagnetic radiation's oscillating electric field. See external applet. Dependent on the frequency, the dipole may move in time to the field, lag behind it, or remain apparently unaffected. When the dipole lags behind the field, then interactions between the dipole and the field leads to an energy loss by heating. Ooh. Difference of these fields. Heating being maximal twice each cycle. The ease of the movement depends on the viscosity and mobility of the electron clouds. In water, these rely on the strength and extent of the hydrogen bond The ease of movement depends on the viscosity and mobility of the electron clouds. In water, these rely on the strength and extent of the hydrogen-bonded network. In free liquid water, this movement occurs at gigahertz frequencies, microwaves, whereas in more restricted bound water, it occurs at megahertz frequencies, short radio waves. So in free liquid water, it's the gigahertz frequencies that can affect these, and and the megahertz in more restricted bound water. And ice, long radio waves, kilohertz. Okay. So gigahertz is microwave, megahertz is short radio waves, and long radio waves is kilohertz, and that's what you do to ice. The reorientation process may be modeled using a wait and switch process where the water molecule has to wait for a period of time until favorable orientation of neighboring molecules occur, and then the hydrogen bonds which switch to the new molecule. Microwave heating has been modeled using the tip 4p FQ potential and is due to the interaction of these moving dipoles. Although molecular vibrations of bimolecules may have microwave frequencies, it is not thought that such resonant coupling is significant due to their low energy compared with thermal energy and the strongly dampening aqueous environment. Okay, let's go to the evaporation of water using high-frequency electric fields. Right, whether they ever made this one or not, I mean, these are things that are doable. 1995, 96. A method for increasing the rate of evaporation of water in a humid atmosphere by providing a high-frequency electric field at the evaporating surface of the water. The method is an energy-efficient alternative to attempts to lower the humidity of the air surrounding water to be evaporated. So, what is claimed is a method for evaporating liquid from a liquid surface into a surrounding atmosphere containing a vapor of the liquid. The method consisting essentially of heating the liquid to cause evaporation at the liquid surface at a first evaporation rate, and applying a high-frequency electric field at the liquid surface to cause evaporation at a second evaporation rate, which is greater than the first evaporation rate, wherein the high-frequency electric field has a frequency between 10 kilohertz and 300 gigahertz. 300 gigahertz is the top end of 5G. So heating the liquid to cause evaporation at the liquid surface at a first evaporation rate, and applying a high-frequency electric field at the liquid surface to cause evaporation at a second evaporation rate, which is greater than the first evaporation rate, wherein the high-frequency electric field has a frequency between... Okay, the method of claim 1, wherein the liquid is water. A method of increasing the rate of evaporation of a liquid having a surrounding atmosphere containing a vapor of the liquid. The method consists essentially of the steps: heating the liquid to cause evaporation at a surface of the liquid exposed to the surrounding atmosphere such that evaporation occurs at a first net rate, and applying a high-frequency electric field at the surface of the liquid wherein the application of the high-frequency electric field substantially prevents the vapor from condensing at the surface of the liquid and thereby causes an increase in the rate of evaporation from the first net rate to second net rate that is higher than the first net rate, wherein the high-frequency electric field has frequency between 10 kilohertz and 300 gigahertz. The method of claim 3, wherein the liquid is water. 5. A method for preventing the formation of water droplets in a water vapor. The method consisting essentially of the steps of heating the water to produce water vapor, and applying a high-frequency electric field to the water vapor to prevent water droplets from forming in the water vapor, wherein the high-frequency electric field has a frequency between 10 kilohertz and 300 gigahertz. A method of preventing undesired condensation of water on an internal surface of water evaporation system, consisting essentially of the steps of heating water to produce water vapor within the water evaporation system, and applying a high-frequency electric field at the internal surface of the water evaporation system to prevent condensation of water on the surface, wherein the electric field has a frequency between 10 kilohertz and 300 gigahertz. Background. The following invention releases to a method and an apparatus for increasing the rate of evaporation of water in a humid atmosphere through the application of a high-frequency electric field. In many parts of the world, portable water is a scarce resource. In such areas, it is not uncommon for large quantities of potable water to be supplied through the use of various thermal distillation methods. One of the most efficient currently used distilleries is the so-called flash evaporator, in which water to be evaporated is sprayed on long, hot pipes. However, even in a relatively efficient distillery, a significant problem is the slowing of the rate of evaporation caused by humid air at the evaporating surface of the water. Yes. So as it gets humid on the surface, that slows the rate of evaporation. So you need to keep getting the moisture off to increase the rate of evaporation. So the present invention provides a method for increasing the rate of evaporation of water in a humid atmosphere, preventing the condensation of water on surfaces where it would normally be expected to form, and causing water to evaporate as pure water vapor without the small droplets characteristic of steam. These effects are obtained through the use of high-frequency electric field. The invention is the result of a discovery made during an investigation into the evaporation kinematics of water. During the investigation, water was allowed to evaporate under a variety of ambient conditions, both with and without the application of a radio frequency electric field. It was discovered that the application of an RF electric field at the surface of the water increased the rate of evaporation of the water when the surface of the water was surrounded by a humid atmosphere. So the RF electric field at the surface of the water increased the rate of evaporation of the water when the surface of the water was surrounded by a humid atmosphere. Oh, sure, yeah, it did it. Even though there was a humid atmosphere, the RF electric field was increasing the rate of evaporation. Sure, furthermore, the water vapor from this process was free from steam, droplets, and no condensation on surrounding experimental framework was observed. These effects were the results of the application of the RF electric field. In the method of the present invention, the water to be evaporated is contained in a containment or evaporation vessel such as a boiler or distillery and is heated to a temperature which provides the desired rate of evaporation. The energy for evaporation being delivered by electricity, combustion, or fossil fuels or other conventional means, the evaporation vessel is vented or ducted so as to make use of the evaporated water vapor. So, I mean, yeah, same principle applies, right? This is it's basic stuff. I mean, it's not rocket science to the debunkers and the trolls. Evaporation of water using high-frequency electric fields. Come on. Moving on. What factors affect the rate of evaporation of water? Wind. Wind is the natural movement of air in any given direction. In order to test the effect of wind on the rate of evaporation of the bowl of water in our experiment, we will use a fan and turn it into the bowl of water being used. When evaporation occurs, the water vapor from our bowl will be sitting just above the surface of the water in our bowl and has not yet been evaporated. When wind is added to the environment in which a body of water is in, the molecules of water vapor are rapidly moved from their resting position above the surface of the remaining water to the direction which the wind is facing. The rapid removal of molecules allows for rapid evaporation to occur because there is an increased amount space on the surface area of the remaining watch, which allow the water molecules to evaporate up. How does wind affect evaporation? This also means that with an increased speed of wind, there will be an increased rate of evaporation, as the molecules sitting on the surface of the body of water will be removed and replaced at a quicker rate. Okay, so next, focus. Water molecules need help to evaporate. Each time a liquid, this was 2015, water molecule enters the vapor phase, a coordinated dance of several molecules is involved according to simulations. For a water molecule to evaporate, transition from liquid to gas, it takes a rare sequence of events involving assistance from two other molecules, according to new computer simulations. Researchers watched 500 virtual liquid water molecules and found that one could only escape the liquid phase if impacted at a precise moment by a bound pair of molecules within the liquid. An improved understanding of evaporation could help researchers modeling atmospheric processes that are part of climate change. Heat, by making molecules move more violently with a liquid, can break the hydrogen bonds that normally hold water molecules together, releasing individual molecules to the air. Previous work has established that molecule ejection requires a collective process, the coordinated interaction of three or more molecules rather than simple collision between two. Yet little is known about these collective mechanisms in principle. The crucial interactions could happen in many ways. But Yuki Nagata and colleagues from the Max Planck Institute for Polymer Research in Mainz, Germany, have now shown that such events always involve a common element, a particularly well-timed three-body interaction that seems crucial to delivering enough energy into one molecule to allow it to escape. The team ran computer simulations of 500 water molecules held in a tiny volume. They set up a liquid region, a zone of relatively high density, with molecules close together and many linked strongly by hydrogen bonds. Adjoining the liquid was zone empty of molecules. When they chose a temperature high enough to drive evaporation, the researchers saw, as expected, occasional evaporation events. Random jostling would send a molecule out of the liquid zone and into the empty zone. In their simulations, the team recovered 325 such events. To learn how these molecules gain enough energy to overcome the strong hydrogen bonding, tying them to the other molecules in the liquid, each molecule is typically involved in 3 or 4 such bonds. Nagata and colleagues inspected the molecules' trajectories. They found that an ejected molecule always gained its energy through a precise interaction with 2 other molecules. It always had a violent collision with a fast-moving molecule just prior to leaving the liquid. The fast-moving molecule, further studied, showed, was hydrogen bonded to a third molecule in a way that was crucial to the evaporation process. 2 hydrogen-bonded molecules continually oscillate, moving closer and further apart rapidly with a characteristic frequency. The researchers found that a molecule that would be ejected always collided with a bonded pair at approximately 40 femtoseconds after the pair reached their closest approach. So there's like a repelling action when if it's 40 seconds after their closest approach, then they're going back out. The moment of collision was also the moment when the bound molecules would be moving apart at maximum speed and able to deliver the most energy. Right. Okay. So that's how their results, other researchers suggest, put the evaporation process in a new light. According to theoretical chemist Adam Willards of the Massachusetts Institute of Technology, previous simulation studies have mostly examined the bulk thermodynamics of water evaporation, treating water as a continuum and neglecting effects tied to individual molecules. This paper really dives into the molecular details, says Willard, and has managed to tease out a rather surprising result. Moreover, the team didn't need superior computational tools. There's no special technique at play here, he says, just good physical intuition and a well-executed piece of statistical analysis. This improved understanding of water evaporation may find applications in technologies for reducing unwanted evaporation, the researchers suggest, for example, in stores of purified water. It may also be helpful to geophysicists studying the influence of atmospheric aerosols on cloud formation through evaporation, a process of importance for climate change. Well, there you go. Long-term structural modification of water under microwave irradiation, low frequency. Raman spectroscopic measures. Raman scattering has been used to study the influence of 2.45 GHz microwave on the structure of water. It has been shown that treatment of the distilled water samples by electromagnetic fields leads to long-term changes in the vibrational density of states. It was established that the retention time of structural changes of the water samples depends on the sample volume. The experimental results have been interpreted on the basis of the percolation model. It has been suggested that the change in the chemical composition of the water treated by microwaves can lead to a change in the structure of the percolation cluster formed by the network of hydrogen bonds. The time of the equilibrium structure recovery of the percolation cluster after termination of the microwave depends on the cluster size and is much slower than the recovery in the chemical composition of water. Electromagnetic waves in the microwave range corresponding to ultra-high frequency 1 to 30 gigahertz are widely used in various industrial processes at electronic, food, pharmaceutical, and chemical industry. Microwaves are efficiently absorbed by a number of substances, and therefore they are used primarily for fast and controlled heating. Fast and controlled heating. Right there, okay? At the same time, many researchers are paying attention to the fact that using the common convective type heater and a microwave oven at the same temperature increase may lead to different implications. There are so-called specific effects of microwaves. The first of them, although they have a thermal nature, cannot be reproduced in the common convection heater. These are the effect of overheating, selective heating, temperature gradients on the border, and so forth. The possibility of non-thermal effects of microwaves on the different processes and substances, despite the considerable amount of experimental work, is a subject of a lively debate recently. The mechanisms of this influence is not entirely clear. The energy of single microwave photons, example 3 gigahertz, corresponds to the energy of 10 to the minus third eV, is several orders of magnitude smaller than the energy of chemical bonds. Therefore, a direct effect like photochemical transformation seems improbable. The ability of the alternating field to redirect the interacting polar molecules and to change the activation energy of a chemical reaction is considered as more realistic. Theoretically, there may be other mechanisms of non-thermal exposure, requiring, however, experimental approval. Due to its fundamental and technological significance, the reports on the effect of microwaves on the properties of water and aqueous solutions, which serve as the working medium or mediator in many industrial processes and are an essential component of living organisms, are of particular interest. The experimental investigations in which the non-thermal effects of microwaves have been registered can be divided into two classes. The first case, the object under study is exposed with low-intensive waves when a thermal effect, even taking into account the specific influences, can be neglected. In particular, in 7, it was reported that the conductivity of the sodium chloride, NaCl, aqueous solutions was changed as the result of the treatment of various microwaves with a frequency at 2.45 gigahertz. The amplitude of the electric field component was about 10.4 VM, which eliminates the heating of the sample more than 0.1 Celsius. In another type of experimental work, the non-thermal microwave effects have been observed simultaneously with heat, or at least with their action, but lead to the significant different results. Properties obtained under the influence of microwaves are commonly observed during a long time, but they are absent in the case of conventional heating, so-called memory effect. The typical relaxation processes in aqueous media have a characteristic time of about picoseconds, and it remains unclear by what processes can be configured as slow dynamics. At the moment, an idea of the structure of water as a continuous network of hydrogen bonds forming a single macroscopic cluster is acknowledged to describe the features of the vibrational spectra of disordered media. The ideas of fractal geometry and the theory of percolation are applied effectively. According to the percolation model, water structure at room temperature can be represented as an infinite percolation cluster containing smaller clusters, small groups of molecules, and individual molecules in its cavities. Low frequency Raman spectra provided the information about the structure of the pseudopolymer network of liquids with hydrogen bonds. The results of our experiment show the influence of microwave frequency at 2.45 gigahertz on the low frequency spectrum of water. It is well known that the Raman spectrum of water is a wide frequency range, is very sensitive to temperature. In a low frequency spectral range, the frequency of crossover changes, indicating a corresponding reduction in the size of irregularities. In it was noted that heating leads to the gradual destruction percolation cluster, and at a temperature above T equals 50 degrees Celsius in the low range of functions ceases to obey a power law. Our results suggest the existence of additional, not only caused by heating, perturbations introduced by microwaves and influencing the structure of water. The structure of the hydrogen bond network and the fractal dimension of the percolation cluster may change as a result of the tetrahedral coordination disorders caused by the presence of defects such as those associated with a change of the number of hydrogen bonds of the molecule or change in the local change of the group of molecules. All right, that's good enough for me. Dielectric heating. Dielectric heating techniques date back to the last 20 years of the 19th century, when it was used in the therapeutic method of diathermy, consisting of the internal warming of the human body or its parts by exposure to electromagnetic fields. Hyperthermy. For decades, the 0.3 to 3 megahertz range of medium frequency radio waves of MF band, typically around 0.6 megahertz, was used. After the advent of radio communications technology, medical diathermy was implemented with the adoption of higher frequencies, 10 to 100 megahertz, more energetic and penetrant in biological tissues. Around the first quarter of the century, neodithermy, ultradithermy, Marconi therapy in Italy, etc., and worldwide referred to as shortwave dithermy and shortwave therapy. About 20 years later, microwave technology was introduced in this field, leading to the development of microwave dithermy, heating of dielectrics with radio waves, to which the definition of dielectric heating is often confined, is usually called radio frequency or high-frequency heating. Heating of dielectrics, water, with radio waves, to which the definition of dielectric heating is often confined, is usually called radio frequency or high-frequency heating. It began to find industrial applications in the early 1940s and underwent rapid growth during the next 2 decades. In this technology, frequency are normally in the 3 to 30 and 30 to 300 megahertz interval of high and very high frequencies, or high frequency and very high frequency bands. So 30 megahertz is 3 gigahertz, right? So that's 2.54 is microwaves, so it's in the microwave range. In contrast to radio frequency heating, industrial uses of microwave heating were introduced only in the 1960s when reliable, high power, and reasonably cheap MW generators, microwave generators, became available. Development was comparatively slow and is still in progress. Irradiation frequencies in the 300 to 3000 megahertz. Now we're getting into the 30 gigahertz and 3 to 30. And the 3 to 30 gigahertz ranges, well, that's what I just said, okay, are employed. Ultra high frequency and super high frequency bands, respectively. Frequencies in the 300 to 3000 megahertz range are almost universally adopted, and for such reason, microwave heating is often referred to as UHF heating. Communications and radar purposes dominate both civil and military uses of RF and microwave spectra. Thus, in order to minimize radio interference, only a few precise frequencies with narrow tolerance are allocated under national and international regulations for industrial, scientific, and medical power applications, so-called ISM bands. Frequencies worldwide allowed by the International Telecommunication Unions, ITU. Okay, I'm not reading all that. Besides these, the intermediate microwave frequencies of 896 plus or minus 10, 915 plus or minus 13 megahertz, extensively used since the beginning of the technology, are allocated to the UK and the Americas, respectively. Okay, a few other frequencies are presently under consideration and can be employed with special permission of local administrations. All other frequencies can be used for laboratory as well as for industrial heating purposes, provided that radio emissions are suppressed by careful shielding of the entire apparatus below very low limiting levels fixed or recommended by the International Special Committee on Radio Interference. Even with the free radiation, ISM bands, RF, and microwave leakages are subject to severe restrictions and controls by inspective authorities because of the health hazards derived from prolonged or repeated exposure to high-frequency electromagnetic fields. So there you go, that. Okay, wait. Even with the free radiation, ISM bands, RF, and microwave leakages are subject to severe restrictions and controls by inspective authorities because of the health hazards derived from prolonged or repeated exposure of high-frequency electromagnetic fields. Health hazards, let's see what they say. Science Direct. I mean, we've got stuff already. Oh, they just list health hazards. Okay. Applicators for microwave technology above 500 megahertz, 5 gigahertz, by contrast, include resonant cavities, traveling wave devices, horns, they're hybrids. Okay. Applications to organometallic syntheses. The application of microwave dielectric heating to organometallic and coordination chemistry was pioneered by Mingus and Baghurst in the late 1980s. Oh. That's interesting. Mingus and Baghurst, huh? Organometallic. What's organometallic? Let's see. There are 5 patents that are covered in this. Okay, this chapter describes organometallics. 5 patents. Patents include aryl borates, boric ester synthesis method for producing. Okay, what organometallics? We're going to look. Relating to or being an organic compound that usually contains a metal or metalloid bounded directly to carbon. Okay. Bonded to carbon. Alright, so, okay, so, alright. Okay, so organometallic coordination chemistry was pioneered by Mingos and Baghurst in the late 80s. Subsequently, it has been demonstrated that a wide range of organometallic synthons may be conveniently and rapidly made in high yields using microwave dielectric heating. Mingos and Baghurst also developed open reflex systems which could adapt from domestic microwave ovens and used safely for the synthesis of organometallic compounds. So mixing metals with carbon. Dielectric heating is based on the use of microwaves or radio frequency waves for heating of insulating material. Okay, microwaves and radio frequency waves. Light and radar waves, the frequency spectrum most commonly used for dielectric heating is in the range of 3 MHz to 30 GHz. For industrial microwaves, the future developments will include high temperature applications with hybrid systems, higher frequency microwaves, and application in chemical processes. Anyways, this is about units here, but magnetic and electric effects on water. Electric effects on water. Water, being dipolar, can be partially aligned by an electric field, and this may be easily shown by the movement of a stream of water by an electrostatic source. Very high field strengths cause water dissociation in liquid water, and hexagonal ice with slightly higher field strengths, causing continued proton flow in ice. Strong electric fields have complex effects on ice formation and dissociation. This will affect the hydrogen bonded network in an anisotropic manner. Alright. I'm going to have to go back to this one. Applications of radio frequency heating in environmental technology. Direct dielectric heating with radio frequency electromagnetic fields is used to optimize a variety of processes in environmental technology, namely soil remediation by soil vapor. Soil remediation by soil vapor extraction or biodegradation, adsorptive, catalytic off-gas treatment, thermal regeneration of drying agents in biogas or natural gas treatment, and decontamination and or drying of brickwork. Okay, it's not exactly on water. Applications of radio frequency heating in environmental technology. We can close that. Radio frequency heating in environmental technology. Direct dielectric heating with radio frequency electromagnetic fields is used to optimize a variety of processes in environmental technology. Okay, so high frequency heating, thermopedia. Radio frequency and microwave are sometimes used as alternatives to convective, conductive, or radiant heat transfer for the processing of nonmetals. Langton, 1949. So they knew that in 1949, okay, which was after Tesla's death and after the war and before they started naming the storms, when they were experimenting with radar. At that time, they knew this. The perceived advantage of dielectric heating is based on the so-called volumetric effect arising from the fact that the energy is absorbed directly in the body of the material rather than being transferred to it via the surface. The concept of volumetric heating needs to be qualified since there is in reality a limited penetration depth which depends on the properties of the material being heated as well as on the wavelength of the energy source. At the shorter wavelength associated with microwave penetration, depth into a wet body is normally a few centimeters. At the longer wavelengths of radio frequency, the depth can be a large fraction of a meter or a few centimeters depending on the ionic conductivity of the water in the material. Okay. Dielectric process heating uses the frequency range from about 5 MHz to 5 GHz with radio frequency, RF being normally defined as being less than 100 MHz. The definition of microwave usually is between 500 MHz and 5 GHz. I thought 500 MHz was 5 GHz. I'm confused. Okay. Within these ranges, there are specific frequencies allocated for industrial, scientific, and medical uses, the so-called ISM bands. The most common of these are 13.56 and 27.12 megahertz for RF with 900 megahertz and 2.54 gigahertz, being the permitted frequencies for microwave. These particular frequencies have been chosen in order to minimize the risk of interference with telecommunications by either the fundamental or by higher harmonics, and have no particular significance as far as the resonance of the water dipole is concerned. Oh, okay. So it's not the frequency that does affect water dipoles. It's just the one that they chose. There's other frequencies that affects a dipole. The frequency within a 900 band varies from country to country depending on local regulations. Okay, heat transfer. Dielectric heat transfer depends on a number of polarization effects which take place over a broad band of frequencies. The most commonly described one is dipolar orientation polarization. This can be seen from Figure 1, which shows less factor as a function of frequency. This is important at microwave frequency, but of relatively little significance at the lower radio frequencies. Dielectric heat transfer depends on a number of polarization effects which take place over a broad band of frequencies. Okay. The most commonly described one is dipolar orientation polarization, Hasted, 1973. Dielectric heat transfer depends on, okay, as can be seen from Figure 1, which shows loss factor as a function of frequency that is important at microwave frequency, but of relatively little significance at the lower radio frequencies. The dominant mode in the RF range is space charge orientation, which in turn is dependent on the ionic conductivity of the material being processed. If the dielectric properties of a particular material are known, it is possible in theory to choose the most appropriate frequency from those available in the ISM bands. In reality, unless the dielectric loss factor is very low, most products can be dried or processed by either RF or microwave. The choice can then be made on other considerations such as the engineering required to make a satisfactory heat transfer applicator compatible with the process line requirements, i.e. product width, height, and shape. Free dipoles, ionic conductivity, RF. Mass transfer considerations. RF and microwaves are alternatives to conventional heat transfer with several features which need careful consideration. Internal mass transfer may be in liquid or vapor phase depending on the structure of the material. For example, in certain capillary porous materials, in the internal generation of heat, having first reduced the viscosity and surface tension of the bulk of the free water in the body, will then cause a small quantity to be evaporated, raising the internal vapor pressure sufficiently for liquid phase flow to occur. In other materials where the pore structure is coarser, the more conventional mechanisms of evaporation followed by vapor phase flow take place. Perhaps the most significant aspect of this form of heating is that moisture gradients are avoided because the heat is transferred directly to the water and is not dependent on the thermal conductivity of the substrate, and consequently, the classic model of drying on a retreating wet front does not apply to this form of heating. Because the surface moisture content is normally at least as high as the average in the body, and the vapor pressure difference across the surface is such that a relatively modest airflows are required. Because the heating arises from the interaction between the high-frequency field and the product, there is no incidental heating or the oven metalwork or the air. In processes which involve the evaporation of water, it is important that recondensation is avoided. The minimum requirement is a flow of heated air over the product to act as a means of mass transfer from the surrounding atmosphere. The same airflow is used to maintain the metalwork above the dew point. Industrial microwave heating has been used extensively in the rubber industry for curing and preheating prior to molding. In the food industry, it has been used for tempering, melting, cooking, and drying. Recently, microwave vacuum dryers have been developed for drying expensive, high-quality, temperature-sensitive pharmaceuticals. A 1995 study, which is the year after Doppler, the last round of Dopplers finished rolling out, effect of ordinary frequency high electric fields on evaporation and drying. And let me not forget, the microwave-induced plasma promoted dielectric heating metrology and application to the photocatalytic to the photocatalytic activation of water, pioneering research and skills, details of grant. There's a clear and effective need for the synthesis of new materials that can sustain and develop future technologies and underpin modern society. To increase the diversity of materials accessible, it is necessary to develop new synthetic techniques. The proposed research describes the application of microwave radiation to provide energy to drive chemical reactions between solids and or between solids and gases. So from water to the air. A confined gas, when exposed to microwave radiation, can ionize, giving rise to a microwave-induced plasma, MIP, that can be used to provide heat, to drive reaction between bulk solids, and as a source of reactive gas species that can chemically modify material. Many popular liquids, example water, and some solids do interact directly with microwaves, causing rapid heating and reaction. Well, pretty simple there. But many technologically important materials are transparent to microwaves at room temperature, thus preventing use in reactions. However, direct microwave dielectric heating is temperature dependent, and many materials will directly couple with microwaves at elevated temperatures. Unfortunately, quantitative data enumerating the temperature dependence of dielectric heating for most solids is not currently available. I guess they figured that out when they took care of Paradise. Here's another application for microwave swing regeneration of aqueous monoethanolamine for post-combustion CO2 capture. So post-combustion carbon capture is a key component of the fight against global warming and climate change. In the narrative as it stands, yes. Not in climate changed as we know it and have proved it. At least what is being cited as climate change, I have proven is weaponized weather beyond a reasonable doubt. It's love affair with Doppler radar, the history that overlaps with it, as we're still unfolding it and telling it as we speak, hasn't been answered to. And so therefore, the climate change paranoia, hysteria, propaganda, fear-mongering, we're all gonna die! Green New Deal, incomplete narrative, industrialized think tank narrative, CO2-based narrative, which is the wrong narrative since Greta, what is the most primary greenhouse gas on Earth? Greta? Sweetie, sweetie, don't be a puppet for the rich man. Yes, the family. Don't be puppet for rich men. Anthropogenic greenhouse gas emissions are the leading cause of global warming. Yes, and you know what causes anthropogenic greenhouse gas emissions? Of the most prominent greenhouse gas on Earth, ladies and gentlemen, boys and girls. With a primary contributor, CO2. No, it's not. Water vapor. Water vapor is moving around. You got Virga dehydrated underneath some clouds, and so the rain just like lingers there. That's because Dopplers dried out the air to a certain amount. Anywho, yeah, microwave-induced plasma. When was this? 2007. Summary of Gland application for key findings. Okay. Oh. Study class, right? Rapid evaporation of hot water can lead to A, superheated steam, B, the formation of ice, C, both of these, D, neither of these. Rapid evaporation of hot water can lead to the formation of ice. So keep that in mind for later on when we talk about ice supersaturated regions or supercooled regions. Because when you hit something with frequency and then you back off, there's a supercooling that can take place. So bookmark that. Rapid evaporation of water sprayed on metallic media beds. Oh ho ho. All right. University of Toronto. Rapid evaporation of water from steam for steam generation can be achieved by spraying liquid droplets on heated metallic surface. This paper describes an experimental study to measure the rate at which water sprayed on the surface of a metallic media bed evaporates. Okay, so now you've got your aerosols, And and if you get your aerosols and the water vapor there, and you hit it with frequency, it evaporates much faster. Right? Right. The impact and evaporation of water droplets on the hot surface is captured using high-speed photography. Anyway, okay. So let's take this one as a case study. This was April 20th through the 21st of 2012. This was a visual that they showed on the website, and just as an example of their composite map, and I thought it was a great example to use because here you can actually see you have a front coming through, and then the Doppler radars build a wall. They bloom out, stopping it from continuing on, and it sends it up instead. See, it's coming across, but the blooms come, and then it breaks it up and sends it out. And this is even illustrated really well on the slower one here. See, this Doppler turns that, takes that line of weather, and because it's right over here, that energy goes like that, goes around it, like it splits it up, like it's a Laffy Taffy being pulled on a line of conveyor belts. You see the Doppler can turn one way, and then it moves the wind. The little red ball is the piece of energy coming through, and the Doppler will... Coming in, coming in, coming in, bloom. Separate, split. Electric weather, 2004. The following excerpts come from a report that appeared in the Institute of Electrical and Electronics Engineers magazine. Spectrum for April. Electric rain-making technology gets Mexico's blessing, but for now doubters prevail north of the border. This is a HoloScience website. From at least the early 1940s to the end of the 20th century, it always rained more in the state of Jalisco in central Mexico than in its neighbor Aguascalientes, since at least the early 1940s, since radar. But in 2000, on a patch of parched pasture in Aguascalientes, since then about as much rain has fallen on the plains of Aguascalientes as on its more lush neighbor. The brainchild of a... Okay, but in 2000, on a patch of parched pasture in Aguascalientes, workers from Mexico City based Electrificación Local de la Atmósfera Terrestre erected a peculiar field of interconnected metal poles and wires, somewhat resembling the skeleton of a carnival tent. The brainchild of a fractious group of Russian emigres, the poles and wires are in fact a network of conductors meant to ionize the air. If the technique is done properly, the thinking goes, the natural current between the Earth and the ionosphere is amplified, leading, through a mechanism that is not fully understood, to rainfall. Well, that's convenient to say it's not fully understood. There are now 17 such installations in 6 states in Mexico, and in January, federal government agencies decided to back construction and operation of 19 more by 2006, potentially altering the weather in much of parched north and central Mexico. Storm clouds gather. Scientists and authorities differ over whether ionizing the air can bring on big weather changes. But some atmospheric scientists aren't so sure the Russians aren't selling snake oil. Ionization is highly unconventional, and in my realm of experience, I've seen no concrete evidence published in a referee journal, nor have I seen sufficient credible eyewitness verification that the technology works as touted, says George Bomar, the meteorologist charged by the Texas government with licensing the state's weather modification project. Comment. This is the common phenomena of cognitive dissonance in science. This is a HoloScience article here. Okay. Cognitive dissonance in science. The Russians are performing a weather experiment which should fail according to accepted theory. So the scientist complains that he has seen no concrete evidence published in a referee journal, but the complaint reduces to a matter of belief. Scientists do not believe electrical power is input to weather systems. Referees who believe atmospheric electricity is an effect rather than a cause of weather would almost certainly find grounds for rejecting funding for or publication of such an experiment. Same applies to the publication of reports from credible eyewitnesses. For decades, airline pilots witnessed strange lightning above storms but were discouraged from reporting it. The objection is unfair and unscientific. Advances come from challenging established beliefs. This is the common phenomena of cognitive dissonance in science. The Russians are performing a weather experiment which should fail according to accepted theory. So the scientist complains that he has seen no concrete evidence published in a refereed journal, but the complaint reduces to a matter of belief. Scientists do not believe electrical power is input to weather systems. Referees who believe atmospheric electricity is an effect, rather than a cause of weather, would almost certainly find grounds for rejecting funding for or publication of such an experiment. The same applies to the publication of reports from credible eyewitnesses. For decades, airline pilots witnessed strange lightning above storms but were discouraged from reporting it. The objection is unfair and unscientific. Why would they be discouraged from reporting it? Advances come from challenging established beliefs. So yes, if it doesn't fit into your narrative, just ignore it, kind of like vaccines. Ionization technology is called either IOLA, ionization of the local atmosphere, by Earthwise or ELAT, electrification of the atmosphere by the company ELAT. IOLA and ELAT compete with conventional cloud seeding, which, though it also remains scientifically unproven, is used in more than 24 countries and 10 U.S. states. Now, I gotta say, I found something in the literature that I don't have digitally. I'm gonna have to pull it up digitally. I have a hard copy of it that shows how successful cloud seeding is, with as yields as much as 13%, or was it even higher? It's at least 13%. So that's a fair increase in yield. To make it actually, it was good enough to extend the monsoon season a few months with a few cloud seeding, really basic cloud seeding experiments during the Storm Fury and Vietnam experiments or applications, because they applied them on the field of the theater of conflict, so to speak. Theater of conflict. Oh, it's a show, all right, huh? Show of no humanity, that's for sure. Okay. They took out bridges, they flooded the area, and then they sprayed them with the Agent Orange. Okay. La 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 la. Cloud seeding usually involves dispersing a chemical agent such as silver iodide into cloud formations, which helps ice crystals form, leading, it is thought, to bigger clouds and more precipitation than without seeding. Well, it is thought that, otherwise they wouldn't be investing so much effort in it, would they? If it was really a known dud, like really a waste of time, it would have stopped a long time ago. But there's something to it, isn't there? There's a little something to it. Besides a lot of liability. Oh yeah, you might make somebody happy with your rain, but the guy next door who lost out on his, he's going to hold you responsible. So there's a liability. I really don't want to know that it works, but you want to keep doing it. Yeah. The ionization approach, according to Bisiashi, now ELAT's vice president in R&D and operations, research and development, does a similar job but twice over. Ions attract water in the atmosphere, creating the aerosol that produces clouds, and they also charge the dust already in the air, making particles become more attractive nuclei for water droplets, which coalesce and fall to the ground as rain. Comment. It seems that the basic problem is gaining acceptance for ionization technology is the facile description of what causes rain, and that is a problem inherited from the experts, the meteorologists and atmospheric scientists. The water molecule is fascinating because, unlike the nitrogen and oxygen molecules in the air, it is electrically polarized. The water molecule is fascinating because, unlike the nitrogen and oxygen molecules in the air, it is electrically polarized. The oxygen blue side of the water molecule is more negative than the hydrogen side red, forming an electric dipole. In an electric field, the water molecule will rotate to line up with the field. When it condenses in a cloud, the average electric dipole moment of a water molecule in a raindrop is 10% greater than that of a single water vapor molecule. So when it condenses in a cloud, the average electric dipole moment of a water molecule in a raindrop is 40% greater than that of a single water vapor molecule. So there's more dipole, so that accumulated, they have a stronger dipole. Okay, the enhancement results from a large polarization caused by the electric field induced by surrounding water molecules. In the atmospheric electric field, the water molecules will be aligned with their dipoles pointing vertically, and in a sense, that is determined by the charge polarization in the cloud. It is interesting to note that the tops of storm clouds are positively charged and the base is negative. That is the reverse of the radial charge polarization within the Earth itself, and it is this charge polarization that gives rise to the lower order attractive force we call gravity. Okay, let's look at that again, This enhancement results from the large polarization caused by the electric field induced by surrounding water molecules. In the atmospheric electric field, the water molecules will be aligned with their dipoles pointing vertically, and in a sense that is determined by the charge polarization in the cloud. It is interesting to note that the tops of storm clouds are positively charged, and the base is negative. That is the reverse of the radial charge polarization within the Earth itself. Oh, is it a mirror? So it is, the tops are positively charged and the base is negative. And it is this charge polarization that gives rise to the low order attractive force we call gravity. I could see that, negative to negative. So it is proposed that water droplets in clouds experience an anti-gravity effect. Wow. It appears to be related to the Bifield-Brown effect, where a charged high-voltage planar capacitor tends to move in the direction of the positive electrode. That effect may explain how millions of tons of water can be suspended kilometers above the ground when cloud droplets are about 1,000 times denser than the surrounding air. Of course, this raises the issue of charge separation in clouds. The conventional isolated Earth view is that positive and negative charge is somehow separated by vertical winds in clouds, and that this process in thunderstorms is responsible for charging up the ionosphere and causing the atmospheric electric field. But this begs the question of cause and effect. Recent high-altitude balloon flights find that charge is not built up in the cloud. It already exists in the ionosphere above. In January 2002, I argued the electric universe model. Thunderstorms are not electricity generators. They are passive elements in an interplanetary circuit. Like a self-repairing leaky condenser. The energy stored in the cloud condenser is released as lightning when it short circuits. Wow. Oh, I'm seeing the universe in a different way already. The short circuits, or a further defined way, this holographic universe, The short circuits can occur either within the cloud or across the external resistive paths to Earth or the ionosphere. The charge across the cloud condenser gives rise to violent vertical electrical winds within the cloud, not vice versa. Okay, the charge across the cloud condenser gives rise to violent vertical electrical winds within the cloud. Wow. Oh. Excuse me a second. I'm just gonna ooh and ah at the realization. 1 second. I'm seeing Tesla at the Wardenclyffe Tower. I'm seeing how the energy is ripping through the air, and that it's not what he does to the air. It's not what he sends to that location or rips from, but it's in that the exchange of these charged areas of the Earth's magnet. Oh, guys. Wow, okay. So the energy stored in the cloud condenser is released as lightning when it short circuits. It means it doesn't get short circuits means it doesn't get a connection. It gets too much. The short circuits can occur either within the cloud or across the external resistive paths to Earth Earth or the ionosphere? So what? It's the condenser? Right. The view accords with a recent report, 17th of November 2003, in Geophysical Review Letters by Joseph Dwyer of the Florida Institute of Technology, which says that according to conventional theory, electrical fields in the atmosphere simply cannot grow large enough to trigger lightning. The conventional view of how lightning is produced is wrong, and so the true origin of lightning remains a mystery. Water vapor in rising air cools and condenses to form clouds. Okay. The conventional explanation for rising air relies upon solar heating. The electrical weather model is an additional galactic energy source, same that powers the sun, to drive the movement of air. It is the same energy source that drives ferocious high-level winds in the giant outer planets, where solar energy is extremely weak. Once the water vapor condenses into water droplets, it is more plausible that millions of tons of water can remain suspended kilometers above the Earth by electrical means rather than by thermal updrafts. The clouds would act to reduce thermals. Although I heard from an Air Force weather observer that the further up you go, the less condensation nuclei there's supposed to be, because there's less air. Well, this would explain how they can change that, huh? Or play with that. Okay. Returning to the article, can we explain how the natural current between the Earth and the ionosphere is amplified and how that might increase rainfall? It seems to follow naturally from the electric weather model because the ion generators are supplying mobile charge carriers into the dielectric or atmosphere, which increases the leakage current between the Earth and the ionosphere. Okay, so that there's all these extra ions in the air is kind of creating these rods of conductivity between the two platelets. And so that makes a leak from the platelets themselves, and they transfer out. So that would be like, okay, the vertical leakage currents drive vertical motion of the air. In some instances, these invisible currents are probably responsible for that unseen danger to aircraft. Ah, that makes sense. Clear air turbulence. And we find the most severe vertical winds in thunderstorms where electrical power is dramatically evident. It's okay. Earthwise installations are structures about 7 meters high, shaped like short, open-topped air traffic control towers that house proprietary ion generators and blowers to lift the ions, separate the antennas, amplify the ionization by manipulating the local electric and electromagnetic fields. ELOT's installations work in the same manner, but are more primitive in appearance, consisting of a 37-meter-high central tower surrounded by 8-meter posts arranged hexagonally at a distance of 150 meters. The tower and posts are interconnected by wires, which, when set to a high DC voltage by a 2-kilowatt generator, ionize air molecules such as nitrogen and oxygen. According to Basiacci, as the ions waft upwards, they produce about 1 milliampere of current. The current swamps the Earth's natural current about 1 picoampere, and can affect the weather up to 200 kilometers from the station, he says. Okay, let's go back here. Earthwise installations are structures about 7 meters high, shaped like short, open-topped air traffic control towers that house proprietary ion generators and blowers to lift the ions. Separate antennas amplify the ionization by manipulating the local electric and electromagnetic fields. Amplify the ionization by manipulating the local electric and electromagnetic fields. Antennas, like radio antennas. ELOT's installations work in the same manner but are more primitive in appearance, consisting of a 37-meter-high central tower surrounded by 8-meter posts arranged hexagonally at a distance of 150 meters. The tower and posts are interconnected by wires, which, when set to a high DC voltage by a 2-kilowatt generator, ionize air molecules such as nitrogen and oxygen. According to Basiacci, as the ions waft upwards, they produce about 1 milliampere of current. The current swamps the Earth's natural current. about 1 picoampere and can affect the weather up to 200 kilometers from the station, he says. Up to 200 kilometers from the station. According as the ions waft upwards, they produce about 1 milliampere of current. Swamps the Earth's natural current about... Okay. Summing up all its tests from 2000 to 2002, ELOT and its U.S. and Canadian counterpart Ionogenics and Marblehead Mass claim that ionization led to about double the average historical precipitation, stimulating, among other things, a 61% increase in bean production in Mexico's Central Basin in the last 3 years. Okay, well, that's a significant, measurable amount. Cloud seeding, in comparison, typically claims only a 10 to 15%. What I say, 13? I know my numbers. And that all convective clouds, non-convective cloud seeding worked, that it's the convective ones that were harder to predict the outcome of. So why didn't, and the paper asks, why didn't they differentiate that in it's a paper that criticizes the scientific community for minimizing weather modification and claiming that it doesn't work. Okay, so within the scientific community, there are people saying, that's intellectually dishonest. Okay, so it's not just me and laymen that are critiquing what's going on. This is non-consensus within the scientific community. Cloud seeding, in comparison, typically claims only a 10 to 15% improvement in rainfall. And even that's effective. Despite the claimed successes, ionization has its critics. Atmospheric scientists contacted for this article noted that even the 4 years of testing was too brief a period to prove that the effects seen were not due to some sort of extraordinary variability in the local weather. Bisiacci claims that the criticism goes to a deeper prejudice. Meteorologists are not used to thinking that electrical phenomena could be important to the normal hydrodynamic model. Meteorologists are not used to thinking that electrical phenomena could be important to the normal hydrodynamic model. See, they're all on a matter universe, not on an electric universe. Weather modification technology has always had a hard time standing up to rigorous scientific scrutiny. Ross N. Hoffman, a vice president at Atmospheric and Environmental Research, Inc. in Lexington, Massachusetts, helped complete a scientific review of cloud seeding, which was released by the U.S. National Research Council. In 2003, it found that even more than 50 years of use, cloud seeding remained unproven from a scientific standpoint. Ionization faces the same problems cloud seeding does, he says. Among those are uncertainty about the natural variability of precipitation, the inability to accurately measure rainfall, and the need to randomize and replicate experiments. The last is particularly troublesome since weather modification companies are typically hired to induce rain whenever they can. Whenever they can. Whenever they can. Randomly turning on or off a system to prove a point is not in the customer's interest, Hoffman notes. Ionization also suffers doubts about its basic plausibility. Brian A. Tinsey, a physicist at the University of Texas, Dallas, and an expert on the effects of ions and current in the atmosphere, points out that the ionosphere is about 250,000 volts positive compared with the ground. Okay. But the effect of the resulting current and changes to it from cosmic rays and other phenomena on droplet formation and precipitation is relatively small and restricted to certain types of clouds in specific locations, he says, considering the size of the natural voltage and the modesty of its impact on rainfall. Effective weather modification using ionization, he believes, would require enormous power input and hundreds of square kilometers of antenna arrays. Considering the size of natural voltage and the modesty of its impact on rainfall, effective weather modification using ionization, he believes, would require enormous power input and hundreds of square kilometers of antenna arrays. Okay, so they don't believe that what we got going on here. All right, Samuel Moore, comment. If conventional theory fails to explain electrical storms, it cannot be used to discount the results of ionization experiments. Instead, conventional theory suffers doubt about its basic plausibility. Weather experts have a limited view of the electrical nature of the Earth and its environment. The enormous power input is freely available from the galaxy. The galactic electrical power drives the weather system on all of the planets and even the sun. So the ionization experiment is rather like the control gate in a transistor, where a small current into the control gate influences the entire power output of the transistor. This method of weather control should eventually force the critics to think again. Whoa. And you know, superheating using Doppler ionizes. Looks like it might be important. In the absence of clouds and rain, the absorption and re-emission of microwave radiation propagating through the Earth's atmosphere are governed by the absorption coefficients for dry air, including molecular oxygen and nitrogen for water vapor. The specification of these two coefficients is functions of radiation frequency, F, frequency in gigahertz, air temperature, dry air pressure, and water vapor pressure, has been the subject of investigation since Becker and Ottler in 1946, Van Vleck 1947, and Birnbaum 1953. Here we investigate these functionalities using satellite measurement of the microwave radiation upwelling from the Earth. Are you using microwaves to measure that microwave radiation? I mean, what I mean, you're not saying solar radiation, you're saying microwave radiation upwelling from the Earth. Let's see what the conclusions tell us. Dry air absorption coefficients, 1989 and 1992. Dry air absorption coefficients. Is this like studying the Doppler rollout? The last dry air absorption coefficients and Rosenkranz's 1998. Vapor absorption coefficients require only a modest adjustment to obtain consistency with satellite observations of the upwelling microwave radiation coming from the Earth's atmosphere overlying the oceans. The water vapor continuum is reduced by 3% to 10% depending on vapor. To accomplish this, significant changes are made to the two components making up the continuum, the foreign and self-broadening parts. The foreign broadening parts is increased by 10% and the self-broadening is decreased by 40% at the higher frequencies. The increase in the nitrogen absorption is a maximum of 20% at the 89 gigahertz. Minor adjustments are made to the 22.235 gigahertz line shape and the non-resonant oxygen absorption. Oxygen absorption. With these adjustments, the agreement between the satellite observations and the model is generally at except for some channels at the absorption values found by this investigation over 5 distinct frequencies. 10.7, 18.7, 23.8, 36.6, and 89 gigahertz. Use the Lieb and Rosenkrantz models to interpolate between these frequencies. Our expectation is that within this range of frequencies, the interpolated model will perform well, having about the same accuracy as at the discrete frequencies. And prediction of rain attenuation, an impact of rain in wave propagation of microwave frequency for tropical region. The most classical approach of determining rain attenuation for radio wave frequency has been to theoretically determine the specific attenuation. At frequency over 10 gigahertz, rain and precipitation can influence the attenuation a lot. The effect of atmospheric attenuation between the source and destination over wireless communication is of major concern, and a proper site visit and proper method are required to control the attenuation level so that the performance can be increased. In this paper, exponential model has been used to determine the attenuation level for K region, India, which can be used for a region having similar condition. The analyzed predicted attenuation data have been compared with ITU, our measured rain attenuation, and the results will provide useful estimation of rainfall attenuation on microwave links in tropical regions that have similar conditions as Almora. Okay. The result of this paper will be helpful for the purpose of efficient microwave link establishment in location, as mentioned in the second section of this paper. Microwave link, as mentioned in the second section of this paper. The importance of proper knowledge of rain attenuation in the designing of a microwave link with rainfall data. Okay, it is a link. Some kind of link with rainfall data which is collected for this experiment Other useful lines of research can be made, although the rain attenuation results are calculated with precise methods. However, more tests and analysis need to be done in order to validate the proposed measures to further understand the physical meaning and existence, and to apply the finding to search for ways of enhancing the system. Microwave signals being used for cell towers are monitored routinely. On the basis of attenuation, the rainfall rate can be achieved. Microwave signals being used for cell towers are monitored routinely. On the basis of database obtained, we can now implement this data to predict rainfall for a given area. So microwave signals being used for cell towers are monitored routinely. Well, holy baloo. Whew! That's interesting. Oh. Microwave signals being used for cell towers are monitored routinely. On the basis of database obtained, we can now implement this data to predict rainfall for a given area. Okay, so because the microwave signals from a cell tower, what database are they obtaining? We can now implement this data to predict rainfall for a given area. How do you predict? The proposed future work in this area may focus on keeping a track on the rainfall status of an area. The proposed future work in this area may focus on keeping a track on the rainfall status of an area by monitoring the level of attenuation obtained from the database. This database can potentially be counteracted by using received signal level data from the enormous number of microwave links used in commercial using received signal level data from the enormous number of microwave links used in commercial cellular communication networks for the Uttarakhand region. This work can be used to monitor the rainfall rate in real time. To monitor those parts of the region where networks of dedicated ground-based rainfall sensors are often virtually absent, it would also decrease the cost of establishment of new rain gauges for measuring the rainfall level. This would help the meteorology and remote sensing department as well. There are many questions still unanswered. 10 gigahertz, 20 gigahertz, 30 gigahertz, 60 gigahertz have been evaluated losing the... Okay. All right, 2.4 gigahertz is absorbed by moisture. A Japanese member posted a research report which says 2.4 gigahertz is absorbed more easily by moisture in the air, and the signal traveling in humid weather is attenuated much faster, shortening its effective range. He's worried about using 2.4 gigahertz RC radio in humid Japan. Is there any truth to this? This is interesting. This is a RC group, right? This guy, yes, that's why a microwave oven will boil water. Do you fly much in fog or rain? Good lift. But the water molecule resonance frequency is about 22 point... Well, now you tell me. I've been flying in the rain and wind for the last 4 months, but boy, now I guess I should quit flying my planes so far away, at least keep them closer like 1,000 feet or so. I guess I'm just a lucky fella. Damn, Spectrum DX6, you would think that the manual would cover this. I have to confess I'm getting a bit bored with all the negativity surrounding the DX6. If you don't like the advancement of the hobby, maybe you ought to stick to rubber-powered free flight. Now that's a real challenge to master. And by the way, I fly whenever I can, and the only challenge is the wind and lack of the light to see by. Good flying. Dick. What negativity? John is just asking a question. I certainly didn't read any evil hidden agendas in his post. What was the question that offended? Worried the 2.4 gigahertz radio in humid Japan would interfere with the signaling of that gigahertz. And look at this guy. This dick. Boy, now I guess I should quit flying my planes. I mean, he just goes like on the attack. Interesting. Okay, I just noticed that. Which was like, and the other guys caught it too. It's like, yeah, everybody has a right to talk here and ask questions. Okay, so He got attacked on that for some reason. But yeah, 2.4 gigahertz is absorbed by moisture. Does that mean it heats it up at all? Well, again, China and Russia band together on controversial heating experiments to modify the atmosphere. The countries are testing a technology for possible military applications, said a Chinese scientist involved in the project. Militaries have been in a race to control the ionosphere, which allows radio signals to bounce long distances for communication for decades. China and Russia have modified an important layer of the atmosphere above Europe to test a controversial technology for possible military application, according to Chinese scientists involved in the project. The Sura base fired up an array of high-powered antennas. See, they've got their own HARP. So we've got supposedly competing fields. And I need to find the piece where Ben Livingston talks about how easy it is to control actually the climate. All you need to do is control 7 intersections of air currents in the world, and you've controlled the global climate. So this is well-studied information. China and Russia getting closer by the day. Communist brother. We are not playing God. We are not the only country teaming up with the Russians. The U.S. military learned from the Russian experiment and built a much larger facility to conduct similar tests. The High Frequency Active Auroral Research Program, or HARP, was established in Gakona, Alaska in the 1990s with funding from the U.S. military and the Defense Advanced Research Projects Agency, DARPA. The HARP facility could generate a maximum 1 gigawatt of power, nearly 4 times that of Sura. Oh, they made a bigger and a better one. But the Russians, they learned it from the Russians. The Russians did it. And where did the Russians get it from? From their native son, the Siberian descent, Nikola Tesla, at the Tunguska event. Such studies must strictly follow ethical guidelines. Whatever they do, it must not cause harm to the people living on this planet. Yeah, well, too late for that. And I'm not blaming it on China here. America's had their own. So ever since the death of Nikola Tesla, when he was, he was debriefed, soaked up of all the knowledge he had nothing more to contribute to society, so then it is my humble opinion, it is my well-researched and humble opinion that he was terminated. So that he wouldn't be a liability. I mean, there's no point in keeping the guy around once you have all that you had from him. They sucked him up and they sent him out. This is the Sura Atmospheric Heating Facility in Russia. Okay, so let's go back here. I gotta see who these guys, I just was Googling and clicked on this article. What is Virga? There's rain on radar, but it's not raining. And this was in response to my Doppler radar atmospheric drying. Okay, using that terminology. And it was just, third down, so I went and looked. What is Virga? There's rain on radar, but it's not raining. It was written, it was posted in 2015 by Chris Robbins and updated a couple years later, or a little over a year later. Okay, the fluid dynamics associated with atmospheric disturbances cause the downstream air ahead of the disturbance before it arrives at a location to rise. Okay, so all the air that's being pushed up to rise behind the disturbance, i.e. after this, and the upstream air behind the disturbance, i.e. after the disturbance has passed, to sink. So something's coming, there's a disturbance, and of course the air's in front is rising while the stuff in the back sinks and takes its place. It's like nature abhorring a vacuum, right? Necessary and sufficient moisture for precipitation is not based on the humidity outside our front door here at ground level. Rather, there must be sufficient moisture in at least 2 critical layers. First and foremost, high moisture content in the layer of rising air. Depth varies. 2. Relative high moisture content between the ground and the cloud base. Since the discussion is about Virga, we are only concerned with the second item, and we will leave the topic of precipitation formation for another day. The second condition listed above requires a layer of air below cloud base to be sufficiently moist for precipitation falling from the clouds to make it all the way to the ground. Okay. layer of air below cloud base to be sufficiently moist, okay, so below the cloud, for precipitation falling from the clouds to make it. So virgas happen because there's a lack of moisture. Right, that second condition listed requires a layer of air below cloud base to be sufficiently moist. So if it's moist, precipitation falling from the clouds to make it all the way to the ground. Okay, so it's dry underneath the virga. And so it's coming down, but it's just lingering because it's dehydrated. That's what's going on, guys. That's why virgas are a relatively new phenomena, this like icky stuff. That my friend, who was a former Air Force weather observer for the National Weather Service, says she doesn't understand the icky goo coming out of clouds anymore. This was a few years ago. I mean, now they're calling it virga. Virga was a lot rarer, I believe, back in the day, and it is a more common phenomena. We used to have more flat bottom clouds. Now it's this icky stuff that goes down. It's the fluid dynamics associated with atmospheric disturbances causes the downstream air ahead of the disturbance before it arrives at the location to rise. The atmospheric disturbances. Here, let me save this real quick. So the fluid dynamics associated with atmospheric disturbances, that's a keyword. Let's just highlight this for a second, right? Atmospheric disturbances. That's what we're calling Doppler radar. That's what we're seeing when Doppler radar pulses. There's a atmospheric disturbance. It is this change of pressures, of temperatures, of conditions, thermo and electric conditions, because it's a frequency, right? So the fluid dynamic associated with atmospheric disturbances cause the down, of course. So if there is a sufficient moisture in the area of rising air, clouds and precipitations may form. Necessary and sufficient moisture for precipitation is not based on the humidity outside our front door here at ground level. Rather, there must be sufficient moisture in at least two critical layers. First and foremost, high moisture content in the layer of rising air. Depth varies. High moisture content in the layer of rising air. Relatively high moisture content between the ground and the cloud base. Since the discussion is about virga, we are only concerned with the second item, and we will leave the topic of precipitation formation for another day. The second condition listed above requires the layer of air below cloud base to be sufficiently moist for precipitation falling from the clouds to make it all the way to the ground. If the air below cloud base is very dry, such as when Doppler radar is being employed, if the air below cloud base is very dry, precipitation will evaporate before reaching the ground. Snowflakes sublimate. Raindrops evaporate. To an observer on the ground, precipitation that is evaporating aloft will appear as streaks extending down from the cloud. See the first image. This is called a virga. Yeah, doesn't quite make it down. So dehydrated. So when virga is occurring, you will see precipitation on radar, but the ground will be dry. Okay. That's because they're evaporating it. You can throw the frisbee, jog with your dog, and do any other normal outdoor activity while rain or snow falls above us. Airplanes will fly through it as they take off or land, and on some occasions precipitation can reach the top of high-rise buildings, but not the sidewalk below. We can see virga streaks in the sky, which remind us that the radar isn't lying. Ah! No, it's not lying. It's just omitting being 100% honest. Huh? Nice iWeatherNet. What is that? iWeatherNet, Illuminati WeatherNet. Okay, so does it mean I don't know anything about these guys. They might be totally fine individuals. I just have a sense of humor about this. And they have a funny logo. What can I say? And then they're explaining something to me, so I should be really grateful, because the science has explained why they all have this icky stuff now. because the radar is evaporating them. So they're in this state of flux, and if it keeps going over and around a radar site, over and around a radar site. Isn't that funny? That's educational. Many times an entire storm system, upper level disturbance, will pass overhead, generating virga, and nary a drop will land on the ground. We can forecast these events accurately most of the time. Forecasting becomes more complicated when there are uncertainties about how heavy the precipitation will be or how long it will last. These considerations are important for the following reasons. If the precipitation is heavy, it can erode the dry layer from the top down. Okay, well then, so you don't have those virgas anymore. Oh, so it adds too much moisture? Okay, if a distance moves slowly enough, it may provide a longer duration of precipitation, which increases the probability that the dry layer will partially or completely erode. Some precipitation may eventually reach the ground. Rain evaporates in dry layer before reaching low elevations. And there you have it, folks. Electromagnetic waves of frequencies between a few kilohertz and some gigahertz are used with radio and radar methods for scientific studies of the Earth's atmosphere, ionosphere environment. The reason for these studies are at least twofold, namely basic research to understand complex phenomena in our environment and the communication-oriented applications. A major contribution to our knowledge of the ionosphere stems from contributions of radar applications operating in this frequency range. These will be briefly summarized in this paper by particularly taking into account most recent developments of systems, methods, and their capabilities for atmosphere-ionosphere research. The Earth's atmosphere and its ionized part, the ionosphere, are dispersive media determined by their refractive indices. Radar and radio methods are applied on certain frequencies, F, in the electromagnetic frequency spectrum. The wave undergoes total or partial reflection in the ionospheric plasma when its frequency is equal to the critical or plasma frequency, which is used with ionosons or high-frequency radars. When the wave frequency is much larger than the plasma frequency, incoherent scatter from thermal motions of free electrons in the ionosphere take place. This is called incoherent or Thomson scatter. Instabilities in the ionosphere generate plasma turbulence, i.e. a direct perturbation of the ionization structure, which cause coherent scatter on HF, VHF, and UHF, high frequency, very high frequency, and ultra high frequency, and is used to study the ENF region irregularities. Clear air turbulence in the natural atmosphere cause small deviations of the refractive index due to density, temperature, and humidity variations, which results in tropospheric and stratospheric irregularities, leading to coherent scatter as well. Ionosphere and atmosphere research with radars. Okay, let's just do conclusions. We summarize the use of a variety of radars for the studies of the Earth's ionosphere and atmosphere. In particular, these techniques are most useful for continuous observations in certain regions, which is not possible with other techniques such as rockets or satellites. It is obvious that the combination of these radar observations with in situ and remote sensing methods with spacecraft combined with models and simulations yield the most complete view of our Earth's middle and upper atmosphere and ionosphere environment. This article can only provide a small review of the most relevant methods using radar to study the Earth's. Okay. Concept and model for utilizing high frequency or radar or microwave producing or emitting devices to produce, effect, create, or induce lightning or light speed or visible to naked eye electromagnetic pulse or pulses, acoustic or ultrasonic shock waves or booms in the air, space, enclosed, or upon any object or mass to be used solely or as part of a system, platform, or device, including weaponry and weather modification. That was 2004. And that's patent US 201-300 15260A1. Microwave Facilitated Atmospheric Energy Projection System, patent US 6111237A. Abstract: the present invention relates to an atmospheric energy projection system for projecting electrical and thermal energy. The microwave facilitated atmospheric energy projection system uses microwave energy at the resonant frequency or frequencies of oxygen and or water to heat the atmosphere. This improves the potential conductivity of the air in the path of the microwave beam by heating the oxygen and water molecules in the air, providing a favored pathway for breakdown. A voltage pulse generator discharges through an electrode positioned near the center of the microwave beam's recent path. A voltage pulse generator discharges through an electrode positioned near the center of the microwave beam's recent path and creates an ionizing wave that follows the microwave beam's recent path. So this is a twofold process. Alternatively, a laser can substitute for the electrode and project a high-powered beam that is focused to create breakdown and thus create the ionizing pulse that travels down the favored pathway. The system can operate in an underwater environment operating at the resonant frequency of water. High-power microwave system employing a phased lock array of inexpensive commercial magnetrons. A high-power microwave generator employing a plurality of inexpensive commercial magnetron tubes cross-coupled by means of a secondary coupling path between each magnetron output pair, whereby a portion of the output energy from the first magnetron tube is injected into a second magnetron tube, and a portion of the output energy from the second magnetron tube is similarly injected into the first magnetron tube. The result, cross-injection of microwave energies, brings the respective magnetron tube pair into a phase lock sufficiently stable to permit coherent combination of their outputs for many high-power microwave applications such as directed energy weapon systems. The magnetron phase lock system requires no external components other than the secondary coupling paths of this invention. A phase lock array. Phase locked. Inexpensive commercial. So you can hit it with a second beam with the Doppler effect. Our radar is affecting the weather. This is from Jim Lee, former Resonated WordPress, and then now shared this from our Radar Operations Center, NOAA. A searchlight mode will be used infrequently for maintenance and testing purposes only. During searchlight mode operation, beam will be directed at a fixed location for up to 5 minutes at a time. We have shown it on for days. Because the beam will be stationary, average power densities will be higher than during normal operation. Average over a 6-minute period, the maximum power density, blah, 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 blah. To prevent violation of the guideline, if multiple 5-minute periods of searchlight mode operation were conducted during a 30-minute interval, the IEEE 1991 guideline for uncontrolled environments could be exceeded. Uncontrolled environments. That's what they're calling it to get people out of there, but they're using that uncontrolled environment mode to manage the environment. To prevent violations of the guideline, each time the searchlight mode is to be used, safety measures will be followed to make significant impacts very unlikely. Well, this is not what we're seeing. And now, meteorologists warn that some of the 5G frequencies could interfere with water vapor signals, meaning less accurate weather forecasts. Electromagnetic absorption by water. Impact of configurations of rapid intermittent assimilation of WSR-88 radar data for the May 8th, 2003 Oklahoma City tornadic thunderstorm case. Centers for Analysis and Prediction of Storms and School of Meteorology. University of Oklahoma, Norman, Oklahoma. 2005 and 6 abstract. Various configurations of the intermittent data assimilation procedure for Level 2 weather surveillance radar. 1988 Doppler radar data are examined for the analysis and prediction of a tornadic thunderstorm that occurred on May 8th. Okay. Several tornadoes were produced by this thunderstorm, causing extensive damages in the South Oklahoma City area. Within the rapidly cycled assimilation system, the Advanced Regional Prediction System, three-dimensional variation data is employed to analyze conventional and radar radial velocity data. High assimilation frequency does not necessarily lead to a better result because, assimilation frequency and in-cloud temperature adjustment scheme should be set carefully to add suitable amounts of potential energy during assimilation. High assimilation frequency does not necessarily lead to a better result because of the significant adjustment during the initial forecast period. When a short assimilation window is used, covering the latter part of the initial stage of storm and using a high assimilation frequency and a temperature adjustment scheme based on latent heat release can quickly build up the storm. Scheme based on latent heat release can quickly. And a temperature adjustment scheme based on latent heat release can quickly build up the storm and produce a reasonable analysis and forecast. Okay, build up the storm in there. viewer. Funny language they use. The results also show that when the data from a single Doppler radar are assimilated with properly chosen assimilation configurations, the model is able to predict the evolution. Oh, yeah. The results also show that when the data from a single Doppler radar are assimilated with properly chosen assimilation configurations, the model is able to predict the evolution of the May 2003 Oklahoma City tornadic thunderstorm well for up to 2.5 hours. The implications of the choices of assimilation settings for real-time applications are discussed. So depending on how they make the settings is how they can predict it. Conclusions. The obtained experimental data allow concluding the long-term changes of the structure of water after the microwave treatment. It is assumed that change in the chemical composition of water treated by microwaves may lead to the changes of percolation cluster formed a network of hydrogen bonds. Okay, it is assumed that change in chemical composition of water treated by microwaves may lead to the changes of the percolation cluster formed network of hydrogen bonds. The recovery time of the equilibrium structure of the percolation cluster after termination of the microwave action depends on the cluster size and is much slower than the recovery of chemical composition of water after termination. So after they shut off the microwave action, the recovery time of the equilibrium structure of the percolation cluster. The obtained experiment data allow concluding the long-term changes of the structure of water. Concluding the long-term changes of the structure of water after the microwave treatment. Wow. I'd like to thank my friend in Amsterdam for this. Conclusions. The obtained experimental data allow concluding the long-term changes of the structure of water after the microwave treatment. So there's a long-term change of the structure of water after the microwave treatment. That means after they hit it with microwave. It is assumed, that's great science, that change in chemical composition of water treated by microwaves may lead to the changes of the percolation cluster formed network of hydrogen bonds. The recovery time of the equilibrium structure of the percolation cluster after termination of the microwave action depends on the cluster size, so how much they pushed it off, and is much slower than the recovery of chemical composition of water. So it has a longer lasting effect. All right. Here's a paper, Microwave Plasma Synthesis of Materials, August 8, 2014. The molecules which are formed by the chemical reaction condense on the few nuclei leading to larger particles. In the case of higher microwave power, a faster chemical reaction rate leads to more nuclei, resulting in a larger amount of smaller particles. So there's a faster chemical reaction, creates more nuclei, a larger amount of small particles. Remember that now that that's a material synthesis process that mimics base aerosol formation in the atmosphere, right? Once you create the nuclei through ice, larger amount of smaller particles. Remember now that's a material synthesis process that mimics base aerosol formation in the atmosphere, nucleation, Aitken, accumulation, course, etc. that then rain or snow down upon your heads. Particle growth does take place in the atmosphere. Common sense. Now we just apply microwaves, plasmas, to speed things up. Yeah, plasmas to speed things up. Okay, and there you have it. Wind waves. When we first noticed the storms interacting with Doppler radar, we first captured this interesting image, thinking that the beams were causing the wave action. It wouldn't be till later on that we nuanced our discovery a little better, realizing that the beams feed the path of the water vapor, but it is the depletion of the Doppler radar within the zone that makes a vacuum of sorts. In nature, it pours a vacuum, and thus the winds and the energies move in towards the center of that vacuum as the energy is depleted. Look, they're depleting, they're depleting it, it's shrinking. It's coming down, so they're not, and then whoosh, the energy comes in across it. Right? Because nature abhors a vacuum. So when that energy that they put in there whoosh, comes down, oh, it's just going to converge right here. Boosh! Right off of there. It's okay. I mean, how many days? I thought this thing was over by now. It was like coming on shore. Look at these beams. They're just staying there. Okay. It's shrinking, right? The energy field goes down and poosh! It all converge. All the energy converges over. And that's a wind. And here everything's coming off of it. Coming off of here. Because this creates moisture too. There comes the plasma wave as it goes down. See, it converges over there. It's puffed out, but it's getting thinner. There it goes. It thins out, and the energy starts converging into it. Nature pours a vacuum. And it wouldn't be till a little bit after that we would notice that these would also be responsible for high and low pressure fronts. Heat islands, if you will.
I was trained adjunct Air Force by the National Weather Service. Now, the technology that we used was 40 years ahead of anything that was sitting in people's homes. And that's par for the course with the military. At each stratum of the atmosphere, which could be 1,000 feet, 5,000 feet, 500 feet, it all depends on what stratum they're looking at. All right? It's very inexact science, believe me. We did not have the red phone to God. The only place that you can predict the possibility of humidity is at base level, which is usually from 0 to 4,000 feet in the air. And that is with 20% accuracy rate. And I'm going to tell you something. None of the clouds that I see on a daily basis are anything like clouds. They're all fake clouds.
Yeah.
Can't even find the bases on a stratus level. They all have this icky goo that comes out from the bottom of every single freaking cloud. I can't tell you where the bases are of a cirrus. I don't know what level. Like right now, I'm looking outside, and I'm trying to determine the base level, which would be my report, as in 5 scattered, meaning 5,000 scattered, 5,000 feet in elevation, scattered. I can't find a bottom.
One day, Doppler radar was down. Product missing. This was a saved website. See my little star here. Product missing. Click here for the KLX status update. This service is no longer available in accordance with the National Weather Service change notice 1616 weather.gov. And raw data. Please see weather.gov and raw data. Oh, so it's funny. So apparently KLIX is down, which is why you can't access the data on that one website that I captured earlier. But it's also one of the days that's like the foggiest. So when there is no activity or a lack of activity, moisture is able to roll in. So all of these little microwaves are propelling outward the moisture, really creating a drought, creating an a lack of precipitation. Not a lot of activity here in our Slidell one. So not only is there fog when Doppler is down, but during the day there's also flat bottom clouds, like our dear Air Force Weather Observer had been missing. Or put another way, when Doppler radar is on, the clouds can't have a flat bottom and can't look like your regular clouds because they are being evaporated.